Since the dawn of humanity, the cosmos has captivated our imaginations. The twinkling stars, the distant planets, the vast expanse of space, all have beckoned us to unravel their secrets. For millennia, we gazed upon the heavens with a mixture of awe and fear, weaving intricate myths and legends to explain the celestial tapestry above. As our understanding grew, so too did our desire to comprehend the universe's fundamental nature. Where did it all begin? What is it made of? And most importantly, what is its ultimate fate? These questions have driven scientific inquiry for centuries, leading to groundbreaking discoveries and revolutionary theories. From ancient astronomers charting the movements of stars to modern-day cosmologists probing the very fabric of space and time, our quest to understand the universe is a testament to the power of human curiosity. The pursuit of this knowledge has not only illuminated our place in the cosmos, but has also reshaped our understanding of physics, chemistry, and the origins of life itself. It is a journey that has taken us to the edge of the unknown, challenging our preconceived notions and inspiring us to reach for ever greater heights of understanding. However, despite the remarkable progress made, the universe retains an air of profound mystery. Even as we celebrate each new discovery, we are constantly reminded of how much more there is to learn. The universe is a vast and complex entity, and our current understanding is still being written. It is this realization, that we are merely scratching the surface of cosmic knowledge, that fuels our ongoing fascination. As we delve deeper into the universe's mysteries, we embark on a journey not just of scientific exploration, but of philosophical and existential contemplation as well. In the mid-20th century, the scientific community found itself at a crossroads in its quest to understand the universe's origins. Two contrasting theories emerged, each offering a radically different perspective on the cosmic narrative. This clash of ideas, known as the Great Debate, captivated the scientific community and the public alike, setting the stage for one of the most exciting chapters in modern cosmology. The first contender, the steady-state theory, proposed a universe with no beginning and no end. Championed by astronomers like Hoyle, this theory suggested that the universe was infinite and eternal, existing in a state of perpetual balance. As galaxies moved apart due to cosmic expansion, new matter was continuously created to fill the gaps, ensuring the universe's overall appearance remained constant over time. This elegant model appealed to a sense of cosmic order and permanence, resonating with those who found the idea of a finite universe unsettling. On the other side of this intellectual battle stood the Big Bang Theory, a revolutionary concept that posited a universe born from a cataclysmic explosion. Proponents of this theory, such as Georges Lemaitre and Georges Gamow, argued that the universe originated from an incredibly hot, dense state billions of years ago. Since then, it has been expanding and cooling, with galaxies forming from the remnants of this primordial fireball. The Big Bang Theory suggested a universe in constant flux, evolving from a simple, energetic beginning into the complex structure we observe today. The debate between these two theories was more than just a scientific disagreement, it was a clash of worldviews. The steady-state theory, with its emphasis on eternity and constancy, offered a comforting vision of a universe that always was and always will be. In contrast, the Big Bang Theory painted a more dynamic picture, one of creation, evolution, and perhaps even an eventual end. This stark contrast sparked heated debates among astronomers, physicists, and philosophers, with each side vying to provide the most compelling evidence for their respective models. The rivalry between the steady-state and Big Bang theories transcended the realm of scientific inquiry. It touched upon fundamental questions about our place in the cosmos and the nature of existence itself. The debate resonated deeply with the public, who were captivated by the possibility of unraveling the universe's ultimate secrets. Newspapers ran headlines proclaiming the clash of titans, and public lectures on cosmology drew large audiences eager to hear the latest developments in the debate. For some, the steady-state theory offered a sense of comfort and stability, the idea of an eternal, unchanging universe resonated with a deep-seated human desire for permanence and order. It suggested a cosmos where our existence, though finite, unfolded against a backdrop of infinite time and space. This perspective resonated with those who found the concept of a universe with a defined beginning and a potential end to be unsettling or even frightening. The Big Bang theory, on the other hand, presented a more dynamic and perhaps more awe-inspiring vision of the cosmos. It suggested that we live in a universe with a rich and complex history, one that began in a fiery maelstrom and evolved over billions of years to produce the stars, galaxies, and ultimately life itself. This perspective resonated with those who embraced the idea of a universe in constant flux, a place where change and evolution were fundamental to its very essence. The stakes in this debate were high, not just for the scientists involved, but for our understanding of the universe and our place within it. The outcome would shape our cosmological worldview for generations to come, influencing how we approached questions about the universe's origins, its evolution, and its ultimate fate. It was a time of great intellectual ferment, a pivotal moment in the history of science where the very foundation of our understanding of the cosmos hung in the balance. The steady-state theory, with its promise of an eternal and unchanging cosmos, held a certain allure for many in the scientific community. It presented a vision of the universe that defied the very notion of a beginning or an end, stretching infinitely in all directions and throughout all of time. This concept, deeply rooted in philosophical and even theological musings throughout history, offered a comforting sense of permanence in the face of an otherwise seemingly chaotic and ever-changing world. Imagine, if you will, a universe where galaxies like celestial ships sail through the vast cosmic ocean. As they drift apart, new galaxies emerge between them, forming from the fabric of space itself. This continuous process of creation and expansion ensures that the universe, when viewed on a grand scale, remains statistically the same throughout eternity. No matter where you look or how far back in time you observe, the universe would, on average, appear much the same. This idea of a universe without beginning or end resonated with those who found the concept of a singular moment of creation, a Big Bang, to be philosophically troubling. The steady-state theory elegantly sidestepped the need to explain what existed before the Big Bang, or what might lie beyond the observable universe. It offered a simple yet profound answer: the universe always was and always will be. There were no perplexing singularities, no moments of cosmic genesis to grapple with, just an eternal and unchanging cosmic expanse. Champions of constancy: Hoyle and the steady-state visionaries. At the forefront of the steady-state movement stood a group of brilliant and somewhat maverick astronomers, united in their belief in an eternal universe. Chief among them was Fred Hoyle, a charismatic and fiercely independent British astronomer known for his sharp wit and unorthodox thinking. Hoyle, along with his colleagues Herman Bondi and Thomas Gold, developed the steady-state theory in the late 1940s, challenging the prevailing wisdom of the time and sparking one of the most significant debates in modern cosmology. Hoyle, a gifted communicator as well as a brilliant scientist, played a pivotal role in popularizing the steady-state theory. He possessed a rare ability to convey complex scientific concepts to the public in a clear and engaging manner. His BBC radio lectures on astronomy, delivered with his characteristic Yorkshire accent, captivated audiences and made him a household name in Britain. It was during one of these radio broadcasts, in 1949, that Hoyle famously coined the term Big Bang to describe the opposing theory, a term initially intended as a derisive jab that ironically became the enduring moniker for the very theory he opposed. Despite his skepticism towards the Big Bang, Hoyle made significant contributions to our understanding of stellar nucleosynthesis, the process by which elements heavier than hydrogen and helium are created within stars. His work in this area, ironically, provided crucial support for the Big Bang theory, as it explained the observed abundance of light elements in the universe. This seeming contradiction highlighted Hoyle's intellectual honesty and his willingness to follow the evidence wherever it led, even when it challenged his deeply held beliefs. A universe in equilibrium, the mechanics of continuous creation. The steady-state theory, while aesthetically pleasing in its simplicity, faced a significant hurdle. It required a mechanism to explain how new matter could be continuously created to maintain the universe's constant density amidst its expansion. To address this challenge, Hoyle and his colleagues proposed the concept of continuous creation, a process by which new matter spontaneously appeared throughout the universe, albeit at an incredibly slow rate. This new matter, they argued, would not violate the laws of physics as we understood them. Instead, it would emerge from the quantum vacuum, the seething sea of virtual particles that constantly pop in and out of existence at the subatomic level. According to the steady-state model, this quantum foam, typically confined to the realm of the very small, could, under the right conditions, give rise to particles of matter on a larger scale, effectively replenishing the universe as it expanded. While the idea of matter spontaneously appearing from seemingly nothing might seem counterintuitive, it was, at the time, a plausible explanation given the limitations of our understanding of the early universe and the nature of quantum physics. The steady-state theory, by incorporating this continuous creation mechanism, offered a self-consistent model of a universe in perpetual equilibrium, where expansion and creation were perfectly balanced, ensuring its eternal and unchanging nature. Philosophical underpinnings, eternity and the human psyche. The steady-state theory's appeal extended beyond the realm of scientific inquiry, resonating deeply with philosophical and even theological notions that had captivated thinkers for centuries. The concept of an eternal and unchanging universe, often referred to as the eternal cosmos or the infinite universe, held a certain allure for those who sought meaning and order in a vast and seemingly indifferent universe. Throughout human history, the idea of infinity has both fascinated and frightened us. It represents the ultimate unknown, a realm beyond our comprehension, yet also a source of wonder and inspiration. The steady-state theory, by embracing the concept of an infinite and eternal universe, tapped into this primal fascination, offering a vision of a cosmos that transcended the limitations of our own finite existence. This philosophical underpinning contributed to the steady-state theory's enduring appeal, even in the face of mounting evidence to the contrary. It offered a sense of comfort and stability, a cosmic reassurance that the universe, despite its apparent complexity and chaos, operated according to a grand and unchanging design. For some, this vision of an eternal cosmos provided a sense of solace, a reminder that our lives, though fleeting, unfolded against a backdrop of infinite time and space. Despite its philosophical appeal and the passionate advocacy of its proponents, the steady-state theory faced increasing scrutiny as new observational data began to emerge in the 1950s and 60s. Astronomers, armed with increasingly powerful telescopes and new techniques for studying the distant universe, began to uncover hints of a cosmic history that challenged the steady-state model's fundamental premise of an unchanging universe. One of the first cracks in the steady-state edifice appeared in the realm of radio astronomy. Scientists studying the distribution of faint radio sources across the sky found a curious discrepancy. There seemed to be a greater number of these sources at very large distances, implying that the universe was not as uniform in time as the steady-state theory predicted. This observation, while not conclusive, suggested that the distant universe, representing an earlier epoch in cosmic history, might have been different from the universe we observe today. Furthermore, the discovery of quasars, incredibly luminous and distant objects powered by supermassive black holes, added another layer of doubt to the steady-state picture. Quasars seemed to be far more common in the distant past, suggesting that the universe had undergone significant evolution since its early epochs. This observation was difficult to reconcile with the steady-state model's assertion of a universe that remained statistically the same throughout all of time. The steady-state theory, with its promise of an eternally unchanging universe, encountered its first significant challenge with the advent of radio astronomy in the 1950s. Astronomers, peering deep into the cosmos with newly developed radio telescopes, began to detect faint whispers of energy emanating from distant galaxies, revealing a universe far more active and dynamic than previously imagined. These distant radio galaxies, many billions of light-years away, held the key to unraveling the universe's evolutionary history, and the data they offered presented a conundrum for the steady-state model. As astronomers meticulously mapped the distribution of these radio sources across the sky, a peculiar pattern emerged. There appeared to be a surplus of these distant radio galaxies compared to their closer counterparts. This observation, subtle yet profound, suggested that the universe's past was not a mirror image of its present. The distant realms of the cosmos, representing an earlier epoch in cosmic history, seemed to harbor a greater abundance of active, energetic galaxies than what we observe in our cosmic neighborhood. This disparity in the distribution of radio galaxies posed a significant problem for the steady-state theory, which hinged on the principle of a universe that remained statistically identical throughout all of time and space. The observed overabundance of distant radio galaxies implied that the universe was not in a state of eternal equilibrium, as the steady-state model proposed, but rather had undergone some form of evolution or change over cosmic timescales. The universe's past, it seemed, was not a static, unchanging tableau, but a dynamic and evolving saga, with earlier epochs characterized by a greater abundance of energetic events and active galaxies. The discovery of quasars in the early 1960s delivered another blow to the steady-state theory, revealing a class of celestial objects that seemed to defy its fundamental tenets. Quasars, short for quasi-stellar radio sources, are among the most distant and luminous objects in the known universe, shining with the energy of trillions of suns, yet occupying a region of space no larger than our solar system. Their discovery sent shockwaves through the astronomical community, challenging existing models of galaxy formation and providing further evidence for a universe in flux. These enigmatic objects, initially appearing as faint star-like points in radio surveys, were soon found to emit prodigious amounts of energy across the electromagnetic spectrum, from radio waves to gamma rays. Their extreme luminosity, combined with their compact size, implied that they were powered by processes far more efficient than anything observed in nearby galaxies. The prevailing theory, which has since been supported by numerous observations, is that quasars are powered by supermassive black holes at the centers of distant galaxies, accreting vast amounts of matter and releasing tremendous amounts of energy in the process. The existence of quasars presented a significant challenge to the steady-state theory. Their abundance in the distant universe, coupled with their virtual absence in the present-day universe, indicated that the universe had undergone a dramatic transformation over cosmic time. The early universe, it seemed, was a far more chaotic and energetic place, teeming with quasars and other active galaxies, while the present-day universe appeared comparatively quiescent. This evolutionary picture, with its clear distinction between past and present, stood in stark contrast to the steady-state model's vision of an eternally unchanging cosmos. The evolutionary narrative challenging the steady-state paradigm. The mounting evidence from radio galaxies, quasars, and other observations painted a compelling picture of a universe in flux, one that evolved from a hot, dense, and energetic beginning into the cooler, more structured cosmos we observe today. This evolutionary narrative, supported by a growing body of observational data, stood in stark contrast to the steady-state theory's static and unchanging universe, forcing proponents of the latter to grapple with the increasingly apparent discrepancies between their model and the observed universe. The emerging picture of cosmic evolution suggested that the early universe was vastly different from the present-day universe. It was a realm of intense activity, where galaxies were still forming, collisions were frequent, and supermassive black holes at the centers of galaxies, such as those powering quasars, were actively feeding on surrounding matter, releasing tremendous amounts of energy. As the universe expanded and cooled, these energetic processes gradually subsided, leading to the more sedate and structured universe we see around us today. This evolutionary perspective, while challenging the steady-state paradigm, aligned well with the predictions of the Big Bang theory. The Big Bang model, with its emphasis on a universe born from a hot, dense state and evolving over billions of years, naturally accounted for the observed differences between the distant and nearby universe. The overabundance of distant radio galaxies and quasars could be explained as relics of a bygone era, a time when the universe was younger, hotter, and more prone to energetic events. The steady-state defense, ad hoc, explanations and theoretical tweaks. Faced with mounting observational challenges, proponents of the steady-state theory, led by the ever-tenacious Fred Hoyle, sought to reconcile their model with the increasingly incompatible data. They proposed a series of modifications and ad hoc explanations, attempting to preserve the essence of an eternal and unchanging universe while accounting for the observed differences between the distant and nearby cosmos. One such attempt involved invoking the concept of local inhomogeneities to explain the overabundance of distant radio sources. Proponents argued that our region of the universe might be unusually devoid of radio galaxies, while other, more distant regions might harbor a greater abundance of these objects. This explanation, however, lacked observational support and seemed rather contrived, relying on the assumption that we occupy a special, statistically unlikely location within the universe. Another line of defense involved proposing modifications to the continuous creation process itself. Some suggested that the rate of matter creation might not be perfectly uniform throughout space and time, leading to fluctuations in the density of radio galaxies and other objects. However, these modifications lacked a strong theoretical basis and often introduced new complexities to the steady-state model, further undermining its elegance and simplicity. A universe in flux, the shifting tide of scientific opinion. Despite the best efforts of its proponents to adapt and modify the steady-state theory, the weight of observational evidence continued to tip the scales in favor of an evolving universe, a cosmos with a history, a beginning, and perhaps even an eventual end. The discovery of the cosmic microwave background radiation in 1965, a faint afterglow of the Big Bang, dealt a decisive blow to the steady-state model, solidifying the Big Bang theory as the prevailing cosmological paradigm. The steady-state theory, once a compelling alternative to the Big Bang, gradually faded from the forefront of cosmological research. Its inability to account for the growing body of observational evidence, coupled with the emergence of a more comprehensive and robust theoretical framework for the Big Bang model, led to its eventual decline. While a few proponents continued to advocate for the steady-state theory, the vast majority of the scientific community embraced the Big Bang as the most plausible explanation for the origin and evolution of the universe. The shift in scientific opinion from the steady-state theory to the Big Bang theory marked a pivotal moment in the history of cosmology. It represented a triumph of the scientific method, where observations and data ultimately guided the development and acceptance of new theories. The Big Bang model, once a radical and even ridiculed concept, emerged as the cornerstone of modern cosmology, providing a framework for understanding the universe's history, its composition, and its eventual fate. A cosmic whisper, the persistent hiss from the heavens. The year is 1964. At Bell Telephone Laboratories in Holmdel, New Jersey, two radio astronomers, Arno Penzias and Robert Wilson, found themselves grappling with a perplexing anomaly in their highly sensitive horn antenna. They were tasked with characterizing radio noise from the Milky Way, a crucial step in developing better communication systems. However, their meticulous efforts were being thwarted by a persistent, low-level hiss that permeated their data, a faint whisper from the cosmos that seemed to defy explanation. At first, Penzias and Wilson suspected a more terrestrial origin for the interference. They meticulously inspected their antenna, a massive horn-shaped structure resembling a giant ear trumpet pointed towards the sky. They meticulously cleaned the antenna, removing a buildup of what they affectionately dubbed white dielectric material, pigeon droppings to be precise, hoping to eliminate the pesky noise. Yet no matter where they pointed the antenna, no matter the time of day or night, the faint hiss persisted, a constant companion in their cosmic observations. The persistence of the signal ruled out any obvious terrestrial sources. It wasn't interference from nearby cities, nor was it emanating from the sun or other known celestial objects. The signal was isotropic, meaning it was coming from all directions with equal intensity, as if the universe itself was bathed in this mysterious hum. The uniformity of the signal was particularly perplexing, hinting at a source that was not localized to any particular point in space but rather permeated the entire cosmos. Serendipity and science, the accidental discovery of the CMB. As Penzias and Wilson diligently pursued every possible explanation for the persistent noise, a serendipitous encounter with another group of scientists would change the course of cosmology. Unbeknownst to them, a team at Princeton University led by Robert Dicke was actively searching for a specific type of cosmic radiation, a faint afterglow predicted by the Big Bang theory. This theoretical radiation, known as the Cosmic Microwave Background, CMB, was thought to be a relic of the universe's hot, dense beginnings, a faint echo of the primordial fireball that birthed the cosmos. Dicke's team had built a dedicated instrument specifically designed to detect this elusive cosmic whisper, but their efforts were initially hampered by technical challenges. Meanwhile, Penzias and Wilson, unaware of the theoretical predictions for the CMB, continued to grapple with their perplexing signal, their meticulous efforts to eliminate it proving futile. The two teams, separated by a mere 60 miles, were unknowingly on the verge of a momentous convergence, their separate paths destined to intersect at the crossroads of serendipity and scientific inquiry. The crucial link between the two groups came through a series of chance conversations and shared connections. Penzias learned of Dicke's work through a mutual colleague and reached out to discuss their findings. This phone call, a seemingly mundane event in the annals of science, would prove to be a pivotal moment, connecting the accidental discovery of an anomaly with the theoretical framework that would explain it. A smoking gun, the afterglow of creation. When Dicke's team received the call from Penzias, they immediately recognized the significance of the persistent noise plaguing the Holmdel antenna. The characteristics of the signal, its isotropy, its temperature of about 3 Kelvin, just a few degrees above absolute zero, matched precisely with the theoretical predictions for the cosmic microwave background radiation. What Penzias and Wilson had stumbled upon, quite by accident, was not merely an annoying hiss, but the long-sought afterglow of creation, the faint echo of the Big Bang itself. The discovery of the CMB sent shockwaves through the scientific community. It was hailed as a smoking gun, a definitive piece of evidence that tipped the scales decisively in favor of the Big Bang theory. The steady-state model, with its premise of an eternal and unchanging universe, offered no straightforward explanation for a ubiquitous background radiation with such a specific temperature and spectrum. The CMB, on the other hand, fit perfectly within the framework of the Big Bang, providing tangible proof of a universe that was once much hotter and denser than it is today. The significance of the CMB extended beyond its role as a confirmation of the Big Bang. The radiation, carrying information from a time when the universe was just 380,000 years old, provided a snapshot of the cosmos in its infancy, a time before stars and galaxies had even begun to form. This baby picture of the universe, encoded in the subtle temperature fluctuations of the CMB, held clues to the universe's composition, its geometry, and the seeds of the large-scale structures we observe today. The discovery of the cosmic microwave background radiation presented a formidable challenge to the steady-state theory. Proponents of the model, who had previously dismissed the Big Bang as a fantastical and unsupported notion, now faced the daunting task of explaining this ubiquitous cosmic signal within the framework of an eternal and unchanging universe. While some steady-state proponents attempted to accommodate the CMB by proposing ad hoc explanations, such as suggesting the radiation originated from distant, unseen galaxies, these attempts ultimately proved unconvincing. The specific temperature and spectrum of the CMB, along with its remarkable uniformity across the sky, defied any straightforward explanation within the steady-state framework. The theory, once a viable contender in the cosmological arena, began to falter under the weight of this compelling new evidence. The steady-state theory, which had initially gained traction for its elegance and simplicity, now faced increasing criticism for its inability to account for this crucial piece of cosmological data. The discovery of the CMB highlighted a fundamental weakness in the model, its reliance on an unchanging universe. The cosmos, as revealed by the CMB, was not a static, eternal entity, but a dynamic and evolving system, bearing the imprints of a hot, dense beginning. The discovery of the cosmic microwave background radiation marked a turning point in cosmology, ushering in a new era dominated by the Big Bang theory. The steady-state model, once a compelling alternative, gradually faded from the forefront of cosmological research, unable to reconcile its fundamental principles with the overwhelming evidence for a universe with a beginning. The Big Bang theory, once viewed with skepticism by some, emerged as the prevailing cosmological paradigm, providing a robust framework for understanding the universe's origin, its evolution, and its large-scale structure. The CMB, a relic of the Big Bang's fiery aftermath, became a cornerstone of modern cosmology, a treasure trove of information about the universe's infancy and the seeds of cosmic structure. The discovery of the CMB not only confirmed the Big Bang but also ignited a new wave of research in cosmology. Scientists, armed with this groundbreaking discovery, embarked on a quest to study the CMB in greater detail, seeking to unravel the mysteries of the early universe and the processes that shape the cosmos we observe today. The hunt was on for subtle variations in the CMB's temperature and polarization, minuscule fluctuations that held clues to the universe's composition, its geometry, and the physics that governed its first fleeting moments. With the Big Bang established as the prevailing cosmological model, scientists turned their attention to constructing a detailed timeline of the universe's evolution, a grand narrative spanning billions of years, from the infinitesimal to the immense. This cosmic chronology, meticulously pieced together from theoretical calculations, computer simulations, and a wealth of observational data, charts the universe's journey from a state of unimaginable heat and density to the complex tapestry of stars, galaxies, and planets we observe today. Imagine, if you will, a cosmic clock set ticking at the moment of the Big Bang. In the first fleeting fractions of a second, the universe undergoes a period of rapid inflation, expanding faster than the speed of light. During this epoch, the universe is a seething cauldron of energy, governed by the laws of quantum mechanics, where space and time themselves are subject to wild fluctuations. As the universe expands and cools, the energy that pervades the cosmos begins to condense into particles, a process akin to steam transforming into water droplets as it cools. At around 1 second after the Big Bang, the universe has cooled sufficiently for protons and neutrons, the building blocks of atomic nuclei, to form. These particles, initially zipping about at incredible speeds, begin to collide and interact, forging the first light elements: hydrogen, helium, and trace amounts of lithium. This process, known as Big Bang nucleosynthesis, leaves a lasting imprint on the universe's composition, determining the relative abundance of these light elements, a prediction that has been confirmed by observations of the oldest stars and galaxies. The universe's recipe: ordinary matter and the enigmatic dark side. As the universe continues to expand and cool, the protons, neutrons, and electrons that make up ordinary matter settle into a more stable state, Around 380,000 years after the Big Bang, a crucial transition occurs. The universe becomes transparent to light. Before this time, the cosmos was a hot, opaque plasma where photons, the particles of light, were constantly scattered by free electrons. However, as the universe cools, electrons combine with protons to form neutral hydrogen atoms, a process known as recombination. With the fog of free electrons lifted, photons are free to travel unimpeded across the cosmos, carrying with them a snapshot of the universe at this pivotal moment. These ancient photons, stretched over billions of years by cosmic expansion into the microwave region of the electromagnetic spectrum, form the cosmic microwave background radiation, a faint afterglow of the Big Bang that provides a wealth of information about the universe's early history and its composition. Surprisingly, the CMB reveals that ordinary matter, the stuff we are made of, stars, planets, and galaxies, accounts for only about 5% of the universe's total energy density. The remaining 95% is composed of two enigmatic entities, dark matter and dark energy. Dark matter, so called because it doesn't interact with light, makes up about 27% of the universe and is thought to be responsible for the gravitational scaffolding upon which galaxies form and evolve. Dark energy, the dominant component of the universe at about 68%, is a mysterious force that seems to be driving the universe's accelerated expansion, a discovery that has profound implications for the universe's ultimate fate. The accelerating cosmos, dark energy's enigmatic influence. In 1998, two independent teams of astronomers studying distant supernovae exploding stars that serve as cosmic distance markers made a startling discovery. The universe's expansion was not slowing down as expected due to gravity's pull but was accelerating. This unexpected finding, which earned the researchers the 2011 Nobel Prize in Physics, shook the foundations of cosmology and introduced a new enigma to the cosmic puzzle. Dark energy. Dark energy, unlike any known form of matter or energy, seems to be a property of space itself, a repulsive force that counteracts gravity's attractive pull. As the universe expands, the density of ordinary matter and dark matter decreases, but the density of dark energy remains constant, or nearly so. Dark energy makes up about 70% of the universe. This means that as the universe ages, the relative influence of dark energy grows stronger, eventually dominating the cosmic energy budget and driving the accelerated expansion we observe. The nature of dark energy remains one of the most pressing mysteries in modern cosmology. Is it a cosmological constant, a fixed property of space-time as Einstein first proposed? Or is it a dynamic field evolving over time and perhaps interacting with other constituents of the universe? Answering these questions is crucial for understanding the universe's ultimate fate. Will the accelerated expansion continue forever, leading to a cold, dark, and ever-expanding cosmos? Or will dark energy's influence wane, perhaps even reversing course and causing the universe to collapse upon itself in a fiery big crunch? Understanding dark energy is a significant challenge, intertwined with the mysteries of the initial singularity and cosmic inflation. From primordial soup to cosmic architecture, the emergence of structure. While dark matter and dark energy dominate the universe's energy budget, it is ordinary matter, albeit a small fraction of the cosmic pie, that forms the stars, galaxies, and planets that populate the cosmos. Understanding how these structures emerged from the nearly uniform primordial soup of the early universe is a remarkable testament to the power of gravity and the interplay between different forms of matter and energy. The seeds of cosmic structure were sown in the first fraction of a second after the Big Bang, during the epoch of inflation. Quantum fluctuations, inherent to the fabric of space-time, were stretched to cosmological scales during this period of rapid expansion, creating tiny variations in the density of matter and energy throughout the early universe. These minute density fluctuations, though seemingly insignificant, served as gravitational wells, attracting more matter over time and eventually growing into the vast cosmic structures we observe today. As the universe continued to expand and cool, gravity amplified these initial density perturbations. Regions of slightly higher density attracted more matter, leading to a runaway process of gravitational collapse. Over billions of years, this cosmic web of matter coalesced into vast filaments and sheets, interspersed with enormous voids, forming the large-scale structure of the universe. Within these filaments and sheets, denser clumps of matter collapsed further, giving rise to galaxies, each a swirling island of stars, gas, and dust, held together by the inexorable pull of gravity. The Standard Model takes shape. A universe shaped by known and unknown forces. The Big Bang model, incorporating the concepts of inflation, dark matter, dark energy, and the evolution of cosmic structure, has emerged as the prevailing cosmological paradigm, a remarkable synthesis of theoretical insights and observational evidence. This model, often referred to as the Lambda CDM model, stands as a testament to the power of scientific inquiry, providing a comprehensive framework for understanding the universe's history, its composition, and its eventual fate. The Lambda CDM model has successfully explained a wide range of cosmological observations, from the abundance of light elements forged in the Big Bang's fiery furnace to the detailed properties of the cosmic microwave background radiation. It has provided accurate predictions for the large-scale distribution of galaxies, the formation of stars and planets, and even the universe's accelerating expansion. The model's success in explaining such a diverse array of phenomena has solidified its status as the standard model of cosmology, a remarkable achievement in our quest to comprehend the cosmos. Despite its remarkable success, the Lambda CDM model is not without its mysteries. The nature of dark matter and dark energy, constituting the vast majority of the universe's energy density, remains elusive. Furthermore, the model's reliance on the Big Bang singularity, a point of infinite density and temperature at the beginning of time, highlights the limitations of our current understanding of gravity and quantum mechanics at such extreme conditions. These unresolved questions and challenges serve as a reminder that the story of the universe is far from over, and that new discoveries and theoretical breakthroughs may yet revolutionize our understanding of the cosmos. Eyes on the early universe. The quest for cosmic clarity. The discovery of the cosmic microwave background radiation in 1965 marked a turning point in cosmology, providing tangible proof of the Big Bang and ushering in a new era of precision cosmology. However, the initial observations, while groundbreaking, offered a limited view of this ancient light, like viewing a distant landscape through a fogged window. To truly unlock the secrets encoded in the CMB, scientists needed a clearer view, a higher resolution image of this faint afterglow of creation. This quest for cosmic clarity drove the development of increasingly sophisticated instruments, designed to measure the CMB's temperature and polarization with exquisite precision. These instruments, often housed in space-based observatories to escape the distorting effects of Earth's atmosphere, embarked on a series of missions to map the CMB in unprecedented detail, each generation of instruments building upon the successes of its predecessors, pushing the boundaries of our technological capabilities and revealing new layers of complexity in the early universe. The pursuit of these high-fidelity CMB maps was driven by a desire to answer some of the most fundamental questions in cosmology. What were the precise conditions in the early universe? How did the first stars and galaxies form? What is the nature of dark matter and dark energy? The subtle variations in the CMB's temperature and polarization, like brushstrokes on a cosmic canvas, held the key to understanding these fundamental processes, providing a glimpse into the universe's infancy and the seeds of cosmic structure. COBE, a first glimpse of the infant universe. In 1989, NASA launched the Cosmic Background Explorer, COBE, satellite, a pioneering mission that would revolutionize our understanding of the cosmic microwave background radiation, and usher in a new era of precision cosmology. COBE, equipped with 3 specialized instruments, embarked on a 4-year mission to map the CMB with unprecedented sensitivity and angular resolution, providing the first detailed glimpse of the universe as it existed just 380,000 years after the Big Bang. One of COBE's key instruments, the differential microwave radiometer, DMR, was designed to measure the temperature differences in the CMB across the sky. The steady-state theory, which had long since fallen out of favor, predicted a perfectly uniform CMB, a smooth afterglow of an eternal and unchanging universe. The Big Bang theory, on the other hand, predicted tiny temperature fluctuations in the CMB, imprints of the density variations present in the early universe, the seeds of cosmic structure. In 1992, the COBE team announced their groundbreaking results. They had detected the long-sought-after temperature fluctuations in the CMB, variations on the order of just a few parts per 100,000. This discovery, hailed as one of the most significant scientific achievements of the 20th century, provided compelling evidence for the Big Bang theory and the existence of the primordial density perturbations that gave rise to galaxies, stars, and ultimately us. WWMAP, sharpening the picture of the cosmos. Building upon COBE's success, NASA launched the Wilkinson Microwave Anisotropy Probe, or WMAP, in 2001, a mission tasked with mapping the cosmic microwave background with even greater precision and resolution. WMAP, named in honor of cosmologist David Wilkinson, a key member of the COBE team, carried more sensitive instruments than its predecessor, allowing it to detect finer details in the CMB's temperature fluctuations and polarization. WMAP's 7-year mission yielded a treasure trove of cosmological data, providing the most precise measurements to date of the universe's age, composition, and geometry. The mission's high-resolution maps of the CMB revealed the universe to be 13.77 billion years old, with a composition of 4.6% ordinary matter, 24% dark matter, and 71.4% dark energy. WMAP also confirmed that the universe's geometry is flat, meaning that parallel lines will remain parallel, a prediction of the inflationary theory, which posits a period of rapid expansion in the universe's first fraction of a second. WMAP's legacy extends beyond its remarkable measurements of the universe's fundamental properties. The mission's data provided strong evidence for the existence of dark energy, the mysterious force driving the universe's accelerated expansion, and refined our understanding of the inflationary epoch, a period of exponential expansion in the universe's first moments that helped to explain the universe's remarkable uniformity and flatness. The quest for the ultimate map of the cosmic microwave background culminated with the European Space Agency's Planck mission, launched in 2009. Planck, named after the German physicist Max Planck, a pioneer of quantum theory, carried the most sensitive CMB instruments ever built, capable of detecting temperature differences in the CMB as small as a few millionths of a degree. Planck's 9 frequency detectors, cooled to just a tenth of a degree above absolute zero, scanned the sky for over 4 years, meticulously mapping the CMB with unprecedented resolution and sensitivity. The mission's data, released in a series of publications starting in 2013, provided the most detailed and accurate picture of the early universe ever obtained, revealing the subtle imprints of the universe's first moments and the seeds of cosmic structure in exquisite detail. Planck's legacy is vast, providing a wealth of information about the universe's age, composition, geometry, and evolution. The mission's data have refined our understanding of the inflationary epoch, constrained the properties of neutrinos, elusive subatomic particles, and provided new insights into the nature of dark matter and dark energy. Planck's map of the CMB stands as a testament to human ingenuity and our insatiable curiosity to understand the cosmos, a legacy that will continue to inspire and guide cosmological research for decades to come. The study of the cosmic microwave background radiation has revolutionized our understanding of the universe, providing tangible proof of the Big Bang, revealing the universe's fundamental properties and offering glimpses into the cosmos's earliest moments. From the pioneering observations of Penzias and Wilson to the high-fidelity maps produced by COBE, WMAP, and Planck, Each generation of CMB experiments has pushed the boundaries of our technological capabilities and deepened our understanding of the universe we inhabit. The legacy of CMB research extends far beyond the remarkable discoveries of the past. The quest to understand this ancient light continues to drive innovation in instrumentation, data analysis, and theoretical modeling, pushing the frontiers of cosmology and astrophysics. Scientists are now developing even more sensitive CMB experiments, designed to detect the faint signature of primordial gravitational waves, ripples in the fabric of spacetime generated in the universe's first fraction of a second, which could provide further evidence for the inflationary theory and unlock new insights into the nature of gravity itself. The study of the CMB is a testament to the power of scientific inquiry, a journey driven by curiosity, ingenuity, and a deep-seated desire to comprehend the universe we inhabit. From the accidental discovery of a faint hiss to the high-definition maps of the early universe, each step in this remarkable journey has brought us closer to understanding our cosmic origins and our place in the grand tapestry of the cosmos. The story of the CMB, like the universe itself, is still being written, and future discoveries promise to further illuminate the mysteries of the cosmos and inspire new generations of explorers to unravel the universe's deepest secrets. From the fiery cataclysm of the Big Bang to the intricate dance of galaxies across billions of years, the universe has revealed a story of breathtaking grandeur and complexity. The journey from the steady-state theory's vision of an eternal, unchanging cosmos to the triumph of the Big Bang model, supported by a wealth of observational evidence, stands as a testament to the power of scientific inquiry. Yet even as we celebrate these remarkable achievements, we are reminded that the cosmic narrative is far from complete. The universe, it seems, guards its secrets closely, and many profound mysteries remain. Challenges that beckon future generations of explorers to unravel their depths. The nature of dark energy, that enigmatic force driving the universe's accelerated expansion, remains one of the most perplexing enigmas in modern cosmology. What is this invisible hand pushing galaxies apart at an ever-increasing rate? Is it a fundamental property of space itself, a cosmological constant woven into the very fabric of the cosmos? Or is it a more dynamic entity, a field evolving over time, perhaps interacting with other constituents of the universe in ways we have yet to comprehend? The answers to these questions hold profound implications for the universe's ultimate fate. Will the expansion continue forever, leading to a cold, dark, and ever more desolate cosmos? Or will dark energy's influence wane, perhaps even reversing course and causing the universe to collapse upon itself in a fiery Big Crunch? The very beginning of the universe, the moment of the Big Bang itself, remains shrouded in mystery. Our current theories, while remarkably successful in describing the universe's evolution from a tiny fraction of a second onward, break down at the singularity, the point of infinite density and temperature where space and time as we know them cease to exist. What happened before the Big Bang? Was there a prior universe collapsing upon itself to ignite the Big Bang we observe? Or did our universe spring forth from a quantum foam, a realm of unimaginable energy fluctuations, where the very laws of physics as we understand them might have been different? These questions, probing the very edge of our understanding, continue to captivate cosmologists, challenging us to extend the boundaries of our knowledge and perhaps even revise our fundamental understanding of the cosmos. The quest to comprehend the universe is a journey without end, a testament to the boundless curiosity of the human spirit. From ancient sky watchers charting the movements of stars, to modern cosmologists probing the deepest reaches of space and time, we have always sought to understand our place in the grand cosmic scheme. The transition from the steady-state theory to the triumph of the lambda CDM model serves as a powerful reminder that our understanding of the universe is constantly evolving, shaped by new observations, theoretical breakthroughs, and a willingness to challenge established paradigms. The mysteries that remain, from the nature of dark energy to the very beginning of the universe, are not limitations but rather invitations to explore further, to delve deeper into the cosmos's hidden depths. The quest to understand the universe is not merely an academic pursuit, but a profound human endeavor, a testament to our insatiable desire to make sense of the world around us and to find our place within it. The more we learn about the universe, the more we appreciate its sheer scale, its elegance, and its awe-inspiring beauty. As we continue to explore the cosmos, we do so with a sense of wonder and humility, recognizing that we are but a small part of something much grander than ourselves. The journey of cosmic discovery is a shared human endeavor, one that transcends borders and cultures, uniting us in a common quest to understand our origins and our place in the grand tapestry of the cosmos. The story of the universe is still being written, and we, as citizens of the cosmos, have the privilege of contributing to this ongoing narrative through our curiosity, our ingenuity, and our unwavering pursuit of knowledge. The mysteries of the universe are a source of endless fascination, a constant reminder that there is always more to learn, more to explore, and more to wonder about. As we peer into the depths of space and time, we are not just uncovering the secrets of the cosmos, but also gaining a deeper understanding of ourselves, our place in the universe, and the profound interconnectedness of all things. The quest to understand the universe is a journey that will continue to captivate and inspire humanity for generations to come, a testament to the enduring power of human curiosity and our insatiable thirst for knowledge.